Well, welcome to our 12th episode of the PM Blend. I'm Mark Powell. This is Joe Finksler to my right.
Hi there, Mark.
Joe, we're at episode 12.
Yeah, I know. I didn't think we'd make it this far.
Well, I didn't either. But I guess getting to episode 12 now, what's that? That tells us that somebody picked us up for
another season.
Of this.
Yeah.
So, well,
we'll see if we can change that for next season.
We'll see if we can get to season 3. Let's try to get through season 2 first. But
did you have to renegotiate your contract?
Oh, they doubled it.
Yeah, they added another 0 to the front of it, Tom. So, but no, listen, welcome and thanks for rejoining us today. If this is the first time you've seen us, welcome. But today we've got 2 guests with us, backed by popular demand. Tom Finksler. Tom, how you doing today?
Good. How are you guys doing?
Well, we're doing all right. And a first-time guest today, Brian Smith from Abbott. Welcome, Brian.
How you doing, gentlemen?
We're great. And as a first-time guest, you get to be the proud owner of one of our PM Blend
nice. Thank you.
fancy tumblers.
Appears to be empty.
Huh? Well,
Thanks for the thought.
We can fix that right afterwards.
well, I'll tell you what. If we bring you back for another episode, which very likely might happen, at that point maybe we'll fill that tumbler up.
You haven't even heard him yet.
Well, you're right. Yeah. You're right.
Manage expectations.
Yeah, no, I've got high expectations for Brian. But before we get into our topic today, Brian, you want to just talk a little bit about Abbott?
So I'm a engineer with Abbott Furnace Company. We design and build the furnaces used in the powder metal process, among other things. So I was asked to come in and lend a hand here to help you understand the sintering process a little bit.
He's here to give us credibility so that
Yeah, right.
they don't
Right.
listen to you and me.
Yeah, exactly. That's what it is. Yeah. Well, we appreciate having you in today.
Pleasure.
And, I'm looking forward to it. And just so you know, during this whole podcast, we do like to kind of rip on each other. So don't take it personally if we start to give you some jabs. Just it's all in good fun. But what do you think, Joe? We ready to jump into optimizing sintering for quality and performance?
Sounds great.
All right. Well, let's jump right into it here. Brian, I'll start with you. What factors have the greatest impact on sintering quality and consistency?
Things that have the greatest impact are the combination of time, temperature, and atmosphere. And we try to design around that for the product, and we also try to design in repeatability so that your next run is the same as this run, and so on and so forth. And those are the 3 big driving factors in sintering: is time, temperature, and atmosphere.
Okay. So it leads into the second question you kind of touched on a little bit. How does temperature control affect part strength and dimensional accuracy?
Your temperature control and your part strength is going to be defined by the raw material. Different materials are going to require different temperatures, different times at temperatures, and different sintering atmospheres. And the idea for the dimensional accuracy is we want to have a consistent temperature across the belt of the furnace, right? So the part on the left matches the part on the right. If we're stacking, the top part matches the bottom part. We want to have a very consistent atmosphere flow and temperature control over the entire loading area of the furnace.
Okay. So Tom, I'll just kind of jump over here to you for a second. Why is atmosphere management so critical during sintering?
Because during sintering, you have different zones in the furnace, and you want to manage what the dew point is, and you want to be sure you keep air out of the furnace. You don't want that attacking the parts in the high heat zone. So, for instance, in a preheat zone, you want to have maybe a little higher dew point. That's where you remove the lubricants from the compact, and you wash that out the front of the furnace. And then during the the high heat zone, you're going to want to be sure that you have a good low dew point with the temperature, and again, time and temperature control as well. You get the proper bonding of the particles together. You'll get your if there's graphite in the part, you'll get it to form carbon for the steel and the other alloying agents. So you want all of those things to come together properly during that. And then during the cooling zone too, if you're restoring carbon or something, you want to be sure that you have the correct atmosphere in that section as well. And if you're doing a sinter hardened material, you want to be sure you're cooled properly and you're moving that atmosphere the way you want it.
Okay. Joe, I know we touch on some of this in our PM 101s, but from our traditional furnaces, from the front end to the back end, what do we usually say that time is to kind of get through that process?
You just threw a grenade into the traditional furnaces would be a continuous belt furnace.
Right. Sorry.
Okay?
Yeah.
So there's and you could have the others, because we also have the pusher furnace at our facility as well. Traditionally, you're running about 2.5 hours, max 3 hours usually, from front to back on a stainless steel. Bronze, copper-based, 45 minutes, Tom?
Anywhere from probably probably an hour to an hour and a half, depending on what you're
front to back, from the time you load to the time you're pulling them off the backside.
Well, and if it's brass material, it's going to be longer than that.
Yeah.
Probably 2.5 hours or so through the furnace.
Yeah, probably 2.5.
Yeah.
Copper infiltration affect that at all? Is that
It does not. That will infiltrate at the same rate as a normal steel part would as well.
Okay. All right. Well, Brian, what role does material selection play in achieving optimal sintering results?
So depending on the material, we kind of just talked about time in the furnace overall. The material would depend on the furnace that it goes into. A bronze or copper-based non-ferrous alloy, you're going to put into a lower temperature furnace. You're going to sinter between 1600 F. A iron-based or copper-infiltrated product you're going to put into what we would say is more of a standard sintering furnace, the 2100 degree range.
Okay.
And that's going to be the 2.5 hour, 3 hour cycle. And when we get up into stainless steels and higher purity materials, you mentioned your pusher furnace, where you're going to be in excess of 2300 F. And the reason for the pusher furnace is the capability of the stainless steel belt is maxed out around 2100. So we can't put a belt in a furnace that goes to 2300. We would melt the belt. So we go to a pusher furnace. So the material depends on the furnace you would use. A lot of it's raw material dependent.
Okay. And Brian, how do you define and measure sintering success? Like what key metrics matter most?
That's really, I think, customer dependent, right? What you would negotiate with your end parts user, right? Dimensional control is obviously very important to them, right? They want a part that fits and is near net shape to what their application is. That may take other operations post sintering to get that, machining and things like that. Strength of the part, we want to have a good bonded product where the atmosphere part of it's important, right? We don't want a part that's oxidized. We don't want a part that still has lubricant in it that prevents the particle bonding. So we need a good delubing process. We need obviously a good sintering process where we get the required time and temperature to get the proper bonds, which in turn is going to lead to the proper dimensions. So there's a lot of factors involved, and it kind of gets into the quality aspect of between you and your customers, what you've negotiated as a good product.
Yeah. Seems like it keeps coming back, Tom, to time and temperature, doesn't it?
It's always time, temperature, and atmosphere.
Yeah.
Yep. That's the bottom
If
line.
you could nail those three things down, you're golden.
Yeah.
Right? Makes it easy. Easy day.
So, Tom, how does sintering optimization improve mechanical properties? I think Brian's kind of touched on that already.
Yeah,
So,
he really kind of nailed that.
Yeah.
As we kind of went through that.
Yeah.
It's basically time, temperature, and atmosphere, right?
Right.
So if you nail those, you're going to nail your dimensional control. You're going to nail your metallurgical properties, the physical properties for the material as well. So it's
And at that point, should have parts coming off the furnace to spec, whatever the
Right.
customer specs
correct.
And as we've talked in the past, a lot of people take this for granted. They see the box, they see the parts go in the box, they don't think anything of it, and magically they come out the back end and they work. But there's a lot of science that goes into that, and there's a lot of time and effort to control that.
Right.
And that clarity and that attention to detail matters in the product.
Yeah. Brian, what new technologies or techniques are emerging to improve sintering? Is there anything new on the forefront here that we're going to see?
Yeah, you have some of our new technology in your shop now. So as the powder metal industry evolves, the press guys are always driving for higher densities, more complicated parts to remove cost of machining, and they're able to press near net shape parts. They're also, everybody's pushing the limits on material densities, different lubricants. As the densities increase in the pressing, the lubricant needs to change to be, the tooling gets hotter, so they need lubricants that can maintain a higher temperature and not melt and bleed out and damage the tooling. So as that improves, the sintering needs to kind of keep pace with that. So lubricants that melt at higher temperatures pose a problem, a challenge for sintering, because we have to remove that lubricant to be able to get the proper bonds and mechanical properties of the parts. So some of our new technology is focused on the delubing process. We do a convective delube where it doesn't necessarily take more time, right? We don't want to build longer furnaces that have a bigger footprint. You guys have a problem with slowing the belt speed down to get longer time in the delube process. So we've accepted that challenge to roll out some of our new technology. We call it the Vulcan delube system.
Okay.
And excuse me, that gives more convective flow at a lower temperature to remove that lubricant, so that we can maintain the belt speed at the current levels and the loads and the throughput that's required. So that is one of our biggest challenges. Another technique and technology we use is convective cooling as well. So to eliminate heat treating and post-secondary operations, there's powders and materials available that we can convectively fast quench cool the product after the sintering process in the furnace that would eliminate a secondary heat treat operation.
Okay.
So those are a couple of the new technologies that are out there, and we're always working to develop some different things.
Sure.
In addition to that, not new technology per se, but the way you record your time and temperatures over time has evolved from maybe.
One of the biggest advancements is just technology itself, right?
Yep.
I mean, the furnace controls they're all touchscreen HMIs. The PLCs have gotten much more complicated. There's data collection systems. There's, everybody wants that infinite amount of data that they can go back months later and find out, if they have a quality issue. They can pull that data out of the system and see that was there an issue during processing. So just as technology has taken over all our lives, we're implementing that into the process as well.
It's also good for troubleshooting the furnace and stuff. You can readily go back and see what happened in the last hour or hours. If something's going
program
on.
parameters
Right.
in for, we have people that they love our system where they get a text at home at night to tell them that a parameter is gone out of spec, and they can actually react from home through their phone to.
Oh, wow.
Technology is a wonderful and a terrible thing.
Right. Well, I think, Tom, in our case, all that data from those furnaces just gets input right into our Plex system. Is that right?
It gets input, I don't know if it goes into Plex, but we certainly record that.
Yeah.
And we can go back months and years
That's what I thought,
to find out what happened if we should get a concern somewhere along the line.
Right. Well, Brian, last question I have for you is what types of furnaces are commonly used for sintering and why?
So the most popular furnace, the majority of them out there are continuous belt furnaces, and they're designed for the temperature in the atmosphere. Like we said, non-ferrous products are done at a lower temperature, so they're continuous belt. Maximum temperature on them is around 1850 F. And then a typical ferrous sintering furnace in the 2100 degree range, they would have a different insulation package and things on them to get that little higher temperature. Pusher furnaces are common in the industry for stainless steels and higher temperature alloys. As I mentioned, when you get up over 2100, you're kind of pushing the limits of the belt. So a pusher furnace, for people that aren't familiar with them, is just a series of ceramic boats that get pushed through the furnace with a hydraulic arm. Again, they're for higher temperature applications. They're typically 2700 F capabilities.
Okay.
Above that, the insulation and the brick kind of become the limiting factor of going higher than that. There are batch furnaces, box furnaces, basically where you would just load your product in a carrier, push it in, close the door, and run a cycle.
You don't usually see those in a standard sintering operation.
No, they're more of
a tempering or
dryers, tempering, lower temperature kind of things.
So you'll see them in the facility, but they're not normally a production application for the standard sinter. It's got some side operations being done.
I see. Okay. And those stainless steel belts that are on those continuous belt furnaces, how often do those take maintenance, or how often do they need replaced? Because I gotta assume under those temperatures,
we have customers that if they get 30 days out of a belt, they're happy. They don't measure in time; they measure in pounds.
Okay.
If they get 1 million pounds through the furnace on that belt, they're ecstatic.
Okay. So those belts,
and then in the lower temperature,
you could have a belt last
years.
3-4 years.
Yes.
Yeah, on a non-ferrous furnace, will last years. So really, it's application.
Yeah.
It varies. You can measure it by pounds. You can measure it by time. Typically, a sintering furnace, iron 4 to 6 months is about the industry average.
Okay.
So.
All right. Okay. Joe,
I think you're covered most of it, Mark.
I think so as well. I think we'll have this guy back.
Yeah, I think
what
so.
do you think?
Bring him back in. Maybe let's torture him a little more.
I think we can. No, we really appreciate you.
Oh, it's a pleasure being here
Like I said,
and being
I
asked to
think we
join you.
might just ask you back for
Okay.
another episode.
Well, fair warning.
Yeah. Tom, thanks again for joining us.
You're welcome.
Yeah.
You're welcome. Thanks, Brian.
Yeah. And listen, thanks for watching episode 12 today. And, hopefully you'll come back and join us for future episodes. And if not, please do join our socials.